thank you for the introduction and evening everyone.
Evening.
First, I want to show you something that I found in a shop in Wales. This is a gemstone that is supposed to bring you money for the rest of your life.
Nice crystal.
Don't touch it. You will. The stars are not aligned with your aura tonight. I will have to clean it otherwise.
Okay, don't worry. I'll bring you some methanol.
Come on, don't mess with me.
I'm not messing with you.
You're messing with me. If you touch it, I will have to put it in the sunlight to cure it, and the sun is getting down now.
Okay. I think we have a misunderstanding here. To me, this is a crystal with an HCP structure.
Okay, let's stop here. I think we are all you all agree that we are very bad actors, but I can tell you that we are much better scientists. So we are both finishing our PhD at University of Birmingham in the Material Science department. And tonight we want to make you think about crystals and metals in a different way.
So the first thing we need to talk about when we talk about crystals is actually symmetry. Symmetry is everywhere in nature. And
And why does nature do that? Why is it so symmetrical?
Yes, because by saving space, nature saves energy. For example, look at those beautiful plants here. Actually, people were interested in symmetry from the ancient ages, basically.
Oh yeah, do you know Kepler studies symmetry?
No, I don't. I know that Kepler was an astronomer, right? What does he have to do with symmetry?
So, 400 years ago, in 1610, Kepler was looking for the perfect gift for his patron and friend. So he was looking for a gift for someone who basically can buy whatever he wants. So, while walking in Prague in the snow, he realized the crystallographic structure of snowflakes. And he thought, perfect present. This is so small, almost nothing, smaller than a drop, and yet very high significance and very complex. So he wrote that essay, The Six Corner Snowflakes, and 400 years later, scientists are still studying their complexity and diversity.
That's a very interesting story that I didn't know about. Okay, symmetry. We all have an idea of what symmetry is, but a very abstract idea. Crystallographers, who are scientists who study symmetry, need to have some more strict rules in order to define what's symmetric and what's not. Okay. Today I'm going to introduce 4 of them, 4 very common ones. This is translations, reflections, glide, and point symmetry. Let's have a look at each one of them, how they look like. Okay, let's say we have an element, like a pint of beer. Translations. So in translations, we basically translate the element at evenly spaced positions. Yeah, basically that's it. Reflections, as the name says, is when we mirror the object around below a plane, for example here below the horizontal line. Glide is a combination of those two, and it looks basically like footsteps in the snow. And point symmetry, which is a very common one, is when we have an object which remains unchanged when we rotate it around a point.
And when you combine all them together, you create wallpapers, like at your grandma house. So let's just take some examples here. So the first example here, you actually have a lot of mirror symmetries shown in blue. And then if you look at the birds, they look like the footsteps that Anastasia was talking about. So you have those glide symmetry here. And let's take another one that is a little bit more complex. This one has a fourfold symmetry shown in red, and then some mirror symmetry at 45 degrees, and glide axes that are perpendicular to the glide symmetry. And this actually is a very common structure that we have in crystals, and we are studying it a lot. And crystallographer give it the cute name of P4M. Very cute. So I hope now that you will see your grandmother wallpaper in a different way. And actually, artists been studied a lot. Scientists been studying a lot, and artists been doing a lot of wallpapers, like Escher's, that is a Dutch graphical artists that have been doing a lot of wallpapers like this?
Very interesting. So we gave some papers, some patterns around. This is some homework for you. So it's one of these patterns. Don't worry, you don't have to do it now. Okay. It's one of those patterns have one or more types of symmetry. So you can have a look later and see how many of those you can spot.
But be careful, some of them are actually not periodic. To be periodic, you need to find a small area that is all the time the same and repeated indefinitely. And in crystallography, we call that the unit cell. And a crystal is actually a 3D pattern of unit cells that are made of atoms.
Crystals. Crystals are everywhere in nature. And we can find crystals with a very high level of symmetry in nature. For example, salt. We all have salt at home. This is a crystal with a cubic structure. Yeah, it looks like that. It's called FCC. Many people in this room know this. FCC stands for face-centered cubic. And as the name says, is when we have atoms placed at the corners of the cube and also atoms placed at the faces, in the middle of the faces of the cube. Another very common crystal we can find is BCC. It can be found in many metals, for example, iron. BCC stands for body-centered cubic, and basically is when, yeah, it's this one. And basically we have atoms at the corners of the cube again and in the middle of the cube.
Wait, what does metals have to do with crystals?
Okay, that's a very common question from people who don't know. So metals actually have a crystal structure. They're made of teeny tiny crystals which are called grains. In each one of those grains, the atomic arrangement remains the same, and once we reach the grain boundaries, this changes orientation. Actually, I lied to you, they're not always teeny tiny. You can see those grains by bare eye in galvanized steel or copper, or in those props we have here. This is brass, you can pass it around. And this is zinc. The grains look a bit like grayscale or, yeah, brass is yellow, granite floor.
So, and all this, the arrangements, the arrangement, so the size and the shape of the crystals, the arrangement of the atomic of the atoms will dictate the final properties of the material. And a very good example is carbon. Carbon can be so carbon is on your pencil as graphite, and it creates those hexagon shapes that are stuck on top of each other as layers. And this makes the graphite on your pencil very brittle and easy to cleave into flakes. You can also pass it around. But diamond is also made of pure carbon, but because it has a cubic structure, it is very hard and strong in every direction. So that means that with the same elements, depending on the crystallographic structure, we can get very, very different properties. Pass it around.
So, okay, we know that depending on the I'm sorry. Yeah. Okay, I wanted diamond, I forgot about this. Okay, let's say I have a bunch of carbon atoms and I want to make a crystal. Of course, I don't prefer to make graphite, it's boring. I want to make diamond.
Of course.
How can I do this? Can I do this?
So actually, in theory, you should be able to transform graphite into a diamond by applying an extremely high pressure to it. So that means that depending of the condition, depending of the temperature and the pressure, you can transform a material into another. Just think about water. Water, when it falls from the sky, depending of the pressure and the temperature, it can form either rain, hail, snow, basically all lovely British weather.
So exactly the same thing happens with pure metals and alloys. Let's say, for example, the most famous alloy out there, probably steel, which is a mix of carbon and iron. So blacksmiths know for ages that depending on the heating temperature and the cooling rate, they can form an alloy with very different properties. Basically, what people know from everyday experience, metallurgists study in a big depth in order to be able to understand in detail and exploit it in order to form materials with desirable properties. These are only 6 of the numerous interesting microstructures steel can form. Those areas, very nice patterns here you can see, it's not patterns, like shapes, are actually the grains we talked about earlier. You can see that the grain shape differs a lot, and also the size, but you have to trust me about this. Those very different microstructures lead to very different properties. And in order to exploit a material for a specific application, we need a specific property. For example, to make car panels, we want a steel or aluminum that is very formable and strong. We want to make a knife, we want it to be hard. If we want to make a screw, we want it to be strong, etc., etc.
So, of course, the process will influence the mechanical properties, but it will also influence the chemical properties, the electrical properties. In my PhD, it will influence the magnetic properties and even the color. So, okay, we know from here we can see the size and the shape of the grains, but how do we actually know the orientation of the atoms in each grain?
For this, we use diffraction. Diffraction is used on a daily basis by material scientists, but it can also be used by archaeologists, geologists, even biologists. Actually, a thing that many people don't know is that we owe the knowing of the DNA structure due to X-ray diffraction.
So diffraction is when a wave of light is going through a small opening or an obstacle and then bends or spread out, creating the diffraction pattern. And the condition to get this pattern is for the opening to be of similar size as the object, of the laser. So a very easy experiment to do, and I will need you at home, is to take a CD. CD actually have small slits of 1.6 microns. Just as a reference, my hair are 50 microns. So CD, 1.6 microns. The wavelength of the laser is 500 nanometer, which means half a micron. 1.6 micron, half a micron, close enough to diffract. So you can see that the light is actually diffracting. Should I wait a little bit?
Yeah, maybe. Okay. Yeah. Can you see more than one? Yeah, that's because of the diffraction. That's what's happening. We have one beam and then we get... You can see?
I remember doing A-level physics. We'd have like a wire and then a laser, and you'd be splitting it with a wire and get the refraction. It was only at like A-level, so after like high school, just before university.
I can put my legs up there.
And then we had to do a whole experiment of like measuring the distance to the dots on the wall.
You can do that, but you need to know the glass or whatever you use for different.
Yeah, the wavelength.
Yes.
Anastasia told me when to come back.
There's another thing also, is it diffraction? Like you get light and you get rainbow.
Just imagine that you didn't know
That's also
how big are the slits in the
Like with the
CDs.
rainbow.
We can actually
It's not the same
determine
blood
it
frequency,
through some
it's
math
split
and
differently.
some geometry. So if we know the wavelength of the laser or the wave, no matter which kind of wave, we can calculate the small opening or the slits on the CDs. And that's exactly what we're doing. So in crystallography and in diffraction, we are using different type of waves, not a laser, to know the distance between the atoms. So we are using X-rays, for example, that are between 0.3 and 3 nanometers, which is very close to the atomic spacing. We are also using neutron diffraction or electron diffraction, of course.
So I'll tell you a recent story. Okay. It's late evening. I should work for my PhD. I don't want to work for my PhD, so I'm watching YouTube videos about my supervisor. Yeah, good. So I'm watching YouTube videos about diffraction.
Such a nerd.
Yeah, I'm guilty. Okay. So I was scrolling and I found a comment of a person complaining that people in the video did not actually show how diffraction patterns looked like. Okay, fair enough. They look like that. They're not very easy to interpret. But let's take them one by one. Maybe the simpler one is the bottom left one, which actually comes from a single crystal, from X-rays diffracted by a single crystal. And each one of those very symmetric points represent a crystal plane. Crystal plane can be, imagine a cube, one face of the cube, for example. Let's go to more complicated ones. The rings. Oh, I'll use the rings. I like the rings. The rings come from a polycrystal, from a beam diffracted by a metallic sample, for example. Then, of course, we don't hit just one crystal, but we hit many crystals all together, so the spots start shaping into a ring. The last one, which is probably my favorite one, because it looks very beautiful, but yeah, results are also very interesting. Comes from electron diffraction. These are electron diffraction patterns. Each one of the bands represents one of the crystal planes again, and the band intersections represent crystal directions. So So those data are not very easy to understand. Okay, we like those data, but we don't use them. The data we use basically look like that. They're very interesting to us, but probably not very interesting to you to see while drinking a pint of beer, I suppose. Yeah, but that's what we end up processing in the end.
But all metals don't look actually like that, and how fiery wants electron ones, we like it because it creates this kind of patterns, this kind of maps. And we like it because it's very colorful and it's much more straightforward to understand, at least for us. And the way it works, it's through a very powerful software that is spotting the diffraction pattern and creating colors like this. So each grain here is representing one orientation. So that means that every color is one different crystallographic orientation. We like them so much that I even made my Christmas card from them. Last year. Yeah. And we can pass it around as well.
We use them a lot basically, and we're going to show more maps like that later in our talk. But first, okay, we talked a lot about symmetry, high symmetry, symmetry. Okay, but in reality, there's no such thing as single crystal. There are defects everywhere. For example,
for example, this cone, I took this picture at a conference we went together in US in October, and at MSMT. So we took this picture together, and this shows cones, and you can see that the cones are not perfectly aligned together, making linear defects. And those linear defects are called dislocations. And we both actually working on dislocation during our PhDs.
Yeah. And actually, don't think defects are a bad thing. Like all things in life, beauty can be found in the defects. Double meaning. So, what can the motion of dislocations can cause? Okay, it can cause work hardening. Work hardening doesn't say anything to many of us, okay? No, it actually does. For example, imagine a hot day, you're in the sun, yeah, like today, you're in the sun melting, you want some ice cream, okay. You remember you have ice cream in the freezer, and you want to eat it as soon as possible. And then you take the ice cream out, you take a spoon, you dip it in the ice cream, you cannot wait, okay. The ice cream is like a brick, and then you dip the spoon, and instead of eating, you bending the spoon, okay. You destroyed your spoon. It was very easy to bend it, but then you don't want to destroy your spoon, and then you try to bend it back, and you find that it's very, very hard to bend back. And this is because of work hardening. What's happening is that during deforming a metal, plastically deforming a metal, what's happening is that dislocations start moving, but they found barriers at the grain boundaries, and they start piling up, and this pile up you translate as a gain of strength in the metal, but it becomes stronger and stronger until it eventually fractures.
So a big part of a PhD is to understand these defects. And Anastasia, can you explain to us a little bit, can you tell a little bit more about your work on load path effects?
Okay, what's load path effect? Basically, it refers to the response a material has when it's deformed in different ways. Different deformation processes, as we'll see a bit later, lead to different macroscopic and microscopic properties. Let's start. So, in my work, yeah.
So, actually, what kind of diffraction did you use during your PhD?
I used a lot of them. So I've used the X-ray, neutron, and electron diffraction.
Basically, all of them.
Yeah. I've used a lot. Diffraction is my PhD, basically. It helps. It's not my whole PhD, but it's my tool. So as I told you before, electron diffraction. Okay, it's my favorite. Not only because it's beautiful, but because you can directly look at the results and make some interpretations. Let's have a look at this beautiful map here.
So why is this map so different from the one we saw before? Why the colors are so blurred?
Yes, you're right, it's a bit different, and that's what makes it interesting. Actually, this is a sample we pulled apart together with James and Wakib there, Switzerland. So we pulled the sample apart, and those discolorations are actually areas where we have high deformation inside the grain, where the crystal is actually being deformed. These areas are areas of high densities of dislocations also.
And what about those stripes? Are they scratches?
No, I polish well my samples, Anastasia, they're not scratches. Those line bears are a characteristic of this material. They're called twins, deformation twins.
Oh yeah, I do have twins as well.
Yeah. You have parasitic twins, right?
Mm-hmm.
Yeah, you do. We don't have similar. There are many types of twins. These are twins that are formed by deformation. They were not there before we started pulling the material apart. Twins is a different kind of defect, and it cannot be found in every material. They actually make this material very, very strong. It's actually so strong that my friend Peter there, yes, once I told you the strength of his material, and you couldn't believe me until I showed you the actual data. So it's a very good, strong steel. So I told you about load path effect. We care about deformation, the direction of deformation. Let's look at some more maps here. Those are similar. We took them the same way. The only thing is that by processing, we've colored the areas of high dislocation densities, where we can find basically many dislocations, with brighter color. The brighter we go, the more the deformation. So, this is a question for you, now test. Which one would you say it's a material that is deformed? Which one of those two is a deformed material? The other one is non-deformed, I can tell you. So, you can guess.
The red one.
The red, yeah?
Left or right?
Yeah, the right. You're right. Okay, you're getting me. This is good. So the right one has higher deformation. Is the deformed one. Okay. Next question. Between those two, those are both deformed. One is less than the other. Which one would you say is more deformed? Right. Right. Again, you're right. Okay. Last one. It's a bit trickier, so I'll ask Anastasia here. So, which one would you say is more deformed?
Left one, definitely.
Left?
Yeah.
No.
Oh.
No. I tricked you here. But you're right. It looks more deformed. The microstructure looks more, that it has more deformation. But that's the microstructure, exactly. The amount of deformation in those two samples is exactly the same. What differs between those two is the deformation direction, and actually that's what the load path effect is all about. We cannot only study material macroscopically, we need to understand what's happening in the microstructure. Use your diffraction in your research.
Okay. So I am working on a new type of material called magnetic shape memory materials. Basically, they are materials that deform under a magnetic field. And the way it does that is through twins. So we talked about twins before, but my twins are slightly different. So they are actually a characteristic of the material I'm studying. And it is those twins that will either expand or shrink depending on the magnetic field, making the entire structure to deform.
Question. Why do your samples have these funky shapes?
So those samples are actually lattices, and they have this kind of shapes because it's actually not very easy for the twins to activate, and they have a big challenge, and this challenge is the grain boundaries. So we talked a lot about grains, but in my case, I don't like grains. Ideally, I want very large grains or no grains at all, single crystal, ideally, and you can just think about them like little zebras in between fences. They cannot hop to the next grain, so when they move, they are just blocked by the grain boundaries. So ideally, I want something that is called bamboo-like grains, that are grains stacked on top of each other like in a bamboo tree, spanning the diameter of the strut.
How do you make those samples?
So I actually have some samples with me. You can just...
I can
press some of them there?
Yes.
And two here, and one
this
here.
Yeah.
So those are my samples for my PhD. Please bring them all back to me because this is my PhD. And if you can, and this is two other samples, but they are not the same material. You know them. So if you look at them, they are really accurate, and the structure is really fine. And actually, the only way to do such structure is to use 3D printing. And the method I am using is a 3D printing technique that uses a very, very powerful laser that melts metallic powder.
I really like your results. You already know this. So, at this point, we're heading towards the end of the talk. We would like to tell you that we both like crystals very much.
Especially healing ones.
Yeah, especially the ones that bring you money. And by understanding the science behind them, we really appreciate their beauty more.
And by understanding the crystallographic structure, and therefore how they influence their properties, we can shape the materials of the future.
We would like to thank you very much for being here. I would like to thank Pint of Science for having us here. And I hope you enjoy your beer.
Thank you, Hop Garden.
Thank you, Hop Garden.
And if you have any question, we will be very happy to answer, and we will hang around a little bit for some more.
Do the crystals that people roll on their face to remove acne work?
Well, I think it depends. If it has a big FCC structure, maybe.
What's wrong with the FCC?
Actually, I have an FCC structure.
How much magnetic field does it take to...
Oh, that's a very good question. So how much do I need of a magnet to move my structures? Well, they actually don't move yet. But in theory, I need 1 Tesla, which is a lot. Or 0.8 Tesla, which is close enough to 1. Yeah?
Why are you wearing a spacesuit then?
I'm wearing a spacesuit to protect myself because the powder are extremely cancerous.
Yeah?
How many tries does it take to print something and not fall apart?
How many tries it takes to print something?
Yeah, like the little ones that you showed.
Well, depending of the material. So if you work on a material that is very common, like you, no, TNT set is awful as well. But if you work on a material that is quite common and you have a lot of literature on it, you can actually print it easily. But for me, I was the first one working on this type of material, so it took me a year. Yeah, it took me a year to optimize the parameter before having what you have in your hands.
Well, I don't have it anymore.
Yeah, sorry. But this, for example, took me 30 minutes. Oh, even less. This or this. Yeah?
What are the different colours on the diagram?
Which diagram? This one. So those are the electron diffraction. So every color is one orientation of the crystals. So you can, yeah, I don't have the models anymore, but it will just be the way you see
Yeah,
it.
it's like...
Yeah. So this is actually not the structure I have in those, but you will either see the crystal like this, or like this, or like this, etc., etc. And every color is one orientation. Yeah?
What's an application that you would use your metal for?
Which one, hers or mine?
Both.
So mine is mostly automotive, because when you make the car panel, you want something with high formability, because first you need to shape it and look nice without fracturing. So you want to... Normally there's a trade-off, okay, you can't have both strength and ductility, but what maybe it is trying to do is to achieve both by understanding microstructure. So basically, yeah, automotive, but anything with metal forming, basically, yeah.
For me, it's a bit more complicated because they are so new. We don't really know why. So, ideally, we want to. It's a very good actuator. So it deforms extremely quickly. It deforms in less than a millisecond, which is very quick, and with a relatively large deformation. So it will be replacing piezoelectrics. If anyone is familiar with that. Okay.
This one actually has something inside of it. I think it's a chess piece.
That's a very good question. So when I'm applying a magnetic field to my material, it bends in one way, and it stays there, even if we switch off the magnet. The way to bring it back to its initial shape is to put a magnet in the other direction. Yeah.
So is that like flipping the thumb on a magnet? So when you say you can bring the material backwards, is that like using the north rather than the south pole on a magnet?
It will. So actually, it uses a perpendicular or parallel to the metal.